Hey there, welcome to Almond Bread, brought to you by the Institute of Recreational Mathematics, which is basically my flat. In this video, we want to find the mathematically optimal way to approach a traffic light. What does that even mean? Let me elaborate. Okay, so we all know the situation. You're driving along the road, listening to some relaxing metalcore, minding your own business. Suddenly, a wild traffic light appears. It looks at you with its evil red Sauron eye, commanding you to stop. What do? You slow down while still trying to keep some speed, hoping that it will turn green before you reach it, so you can cruise right past it without actually having to stop like an idiot. You're getting closer, but it's still red. Closer and closer, but that bossy piece of light just won't change. Steadily losing hope, you realize that you will have to face the inevitable. You will have to surrender. The traffic light has won. Again. Your foot stands on the brake. It feels like you're choking the last bit of life out of the car. You don't want it, but it has to be done. Next thing you feel is that tiny little rocking back and forth motion that indicates that your car has come to halt. A short moment of silence. You were just starting to rethink the decisions you made in life when that stupid trash can flashes a green middle finger into your face. Full of regret, grief and agony, thinking about the 2 milliliters of fuel you just wasted, you accelerate again. You continue your journey, but you're not the same person anymore. You're empty and broken, your soul bearing yet another scar henceforth. Which is bad enough, but worse yet, you are now frustrated and can't concentrate as much anymore on piloting the potential murder weapon that is your car. You might run over someone who was about to prove Riemann's conjecture or bring peace to the Middle East. A whole butterfly effect of horrible consequences, all because you didn't slow down a tiny bit more so you could have crossed the light without stopping. But it's not that easy. You can only think that now, because now you have hindsight. You couldn't have known in the beginning. In the beginning you were facing a very difficult dilemma. Should you slow down more in order to be slower, in order to give the traffic light more time, in order to make it more likely that it turned green before you reach it? Or should you just coast, keeping all the speed you have, making it more likely that you have to stop, but those few times when you can cross the green light with higher speed make up for all the other occasions of stopping misery? Obviously, someone has to figure out the best way to deal with this terrible, horrible, dreadful problem. Well, don't despair, for here comes Almond Bread to the rescue. We start out by making some assumptions about the situation, as one always does when one wants to model some process. Our first assumption is that the traffic light is initially red. The human brain cannot decelerate when it sees a green traffic light, so no need for investigation there. Next assumption. You just came around the corner and didn't see when the traffic light had turned red, so you don't know when it will turn green again. If you knew, things would be too trivial. We want statistics. Everybody loves statistics. However, you do know the duration of one entire red phase of the traffic light, or at least the ballpark, because we will need that. In order to make life at least a tiny bit easier, we assume that your car can retain its speed perfectly while coasting, so no friction losses. And we won't put a limit on deceleration, so your car can be stopped in an instant if required. Oh, one more very important point. If we want to optimize something, we need some sort of optimization criterion. Usually this is a fitness or a cost function and we want to maximize or minimize its outcome by tweaking the inputs. So let's say in this case, we want to maximize the speed of the car in the moment the light turns green. And I mean on average over several traffic light approaches. Okay, now let's start working things out by finally doing some sweet graphing action. For the horizontal axis, we use the time. On the vertical axis, we will look at the speed. On the left, we set the time to 0, which is when you first see the red traffic light from a distance. On the right, we have the time t-red, which is the duration of one complete red phase and hence the latest possible moment for the traffic light to turn green. On the vertical axis, we start out with the speed v0, which is the speed that you start out with. How does the distance between the initial car position and the traffic light come into play? It limits the integral of your speed curve, or the area under it, if you're not that familiar with integration yet or anymore. I figured that my last video was maybe a bit too heavy for the public, so I'm trying to go Linkin Park and be a bit more mass compatible. Let's look at some possible progressions, shall we? We shall. In the first scenario, you just coast towards the light with unchanged speed until you reach it. You reach it means that the area under the speed curve has reached a certain value, which, as said, corresponds to the track length that was available. If the light has turned green until then, so within this time window here, great. Otherwise, you have to stomp the brake and wait things out. Second scenario. Here you go with the worst case and assume that the light will turn green at the latest possible moment. You decelerate initially until you have a specific speed so that you can coast to the traffic light and it will turn green when you are there. so no need to brake. We have the same area under the curve as before. The third scenario is what most people probably do intuitively. I assume that because it's what I do. You try to keep your foot on the brake in a constant position, so you have constant deceleration until you stand at the traffic light. If it turns green before, cool. If not, well, we've discussed what happens. Of course, you're not limited to those three scenarios. You can basically do anything you want. You could even accelerate or go backwards. The only rule is, if the area below the curve has reached a certain limit which was given by the initial track length, you have to stop if the light is not green until then, assuming you don't want to cross a red light. Now, let's take a look at the thing we wanted to optimize. It was the average speed in the moment the light turns green. Why in the moment the light turns green and not when you drive past it? Because then optimization could cheat. It can just stop the car in the beginning, wait until you have green, and then race towards the light, passing it with blazing speed all the time. But that's not how we intended things. That's cheating. It doesn't make sense in reality. That's right, but optimization doesn't care. Optimization wants to find the optimal solution to the cost function at all, well, cost. It will even spit out weird things like negative time durations or imaginary lengths if that helps. So one has to be absolutely specific with the model and exclude all possibilities for cheating. Maximum average speed in the moment the light turns green felt to me like it could work. So how do we even calculate that? Let's just start with an easy scenario, scenario 1. Coast to the light and stop if it's still red. Let's have a look. Your cruising speed is v0. The time that you can coast is limited by the track length to the traffic light. Since speed is length over time, time is actually length per speed. Good luck wrapping your head around the concept of length per speed. Anyway, the coasting time is LTL for traffic light divided by v0. We can safely assume that the probability of the light turning green at any given moment is equal for all moments on the time axis. Up to the maximum red phase duration, of course. This means the likelihood p of the light turning green within a certain time interval is proportional to its duration. It is 1 for the whole interval t red, so for the coasting duration it is coasting time over red phase, so LTL divided by v0 and t red. We will call that probability p coast. The probability of the light turning green while you are already standing will be p halt. If we want to find the average outcome of our experiment, we have to multiply all possible outcomes with their probability and then add them up. Here there are two possibilities. You either come out of the situation with the speed v0, which is p coast likely, or with 0 speed, where we don't care how likely it is, because it will be multiplied by 0 anyway. So your average outcome speed for this scenario is v0 times p coast, which is v0 times LTL over v0 and t red. Interesting, v0 is cancelled out and we are left with LTL over t red. So you are telling me that the average outcome speed does not depend on the coasting speed? That's freaky. Let's look at the second scenario. You brake right away so that your remaining speed will make you pass the traffic light exactly when it turns green in the latest possible moment. The track length you want to cover at constant speed is L traffic light. The time you have is the maximum red time t red. Hence you have to set your speed to LTL over t red, which, if you think about it, already has to be your average outcome speed. And it is LTL over t red, like in scenario 1. It is a bit strange at first, but on the other hand it's pretty obvious. Because the second scenario is included in the first scenario, since we found that the average outcome speed does not depend on the initial coasting speed. So then let's consider the third scenario. You steadily reduce the speed so that you come to halt exactly at the traffic light, hoping the light turns green before. How hard do you have to brake for that? Crunching the numbers, we obtain that the time at which you come to halt, t halt, equals 2 LTL over v0. And the acceleration is this here, but we don't actually need that. What's your average speed when the light turns green? The likelihood p brake that the light turns green during the deceleration phase is t halt over t red, which is equal to this. But what's the speed? Well, if we listen closely to our mathematical intuition, it tells us that the average value of such a constant slope situation here is the value in the middle, so half v0. Again, the standing phase does not add to the average outcome. So we get this, where we can cancel some stuff out, and we get LTL over t red. Now it's getting uncanny. Alright, well, let's have a look at the general case then. The average is also called mean value and is defined by this integral, where a and b are the limits of the interval above which we want to compute the mean value. So in our case, f is the speed, x is the time, a is time 0, and b is the time t red. So we get 1 over t red times integral from 0 to t red over v of t dt. Fun fact, that integral is exactly the same as the covered track, which is what is set by your initial distance from the traffic light. So now everything makes sense. Well, I don't know about you, but I still find it a bit surprising. It means that you can do whatever you want, the average speed that you have when the light turns green is not affected by it. The only condition is that you have reached the light within the maximum red time. Otherwise the speed integral, which is the covered track, shrinks and so does your mean speed. How does this insight help against the misery of the initial situation? Well, it should drastically ease your mind. Now that you know that in whatever way you approach that red traffic light, it's the mathematically optimal behavior, you can just relax and be zen about it. That attitude is probably very healthy for all other aspects of your life as well, but I won't work out the maths for all that. But wait, what if you don't care about your speed in the moment the light turns green, but about fuel consumption? Well, that's a different story. First of all, you won't accelerate while it's red, because that would be stupid. But apart from that, you want to conserve as much kinetic energy as possible. Kinetic energy is proportional to the square of the speed, so now we want to maximize v squared in the moment the light turns green. So here is your average outcome energy. It's basically an integral over v squared with some factor represented by the Greek scribble. Before, more speed for shorter time and less speed for longer time had identical impact on our cost function. But with speed being squared now, more speed for shorter time suddenly has higher value than longer time with lower speed. So if you want to minimize fuel consumption, the best strategy is conserving the initial speed as long as possible and only braking shortly before you reach the light. The few times where the light turns green before you reach it and you can pass it with high speed make up for all the times where you have to brake. I found that to be totally counterintuitive and highly unsatisfying, I must admit. However, please, when applying this strategy in the real world, please consider that it might also increase the likelihood of the car behind you bumping into you, which should not be neglected in your real-world cost function. Okay, what else can be optimized? Let's assume you want to waste as little time as possible at the light. This is a bit more difficult to optimize, because we can't just optimize the time at which you pass it. If we did that, you would just approach it as fast as possible, you stop at it, then when the light turns green, you instantly hit the accelerator, which means you always pass the light as early as possible. However, this doesn't account for conserved speed. And what you actually care about is the time that you reach the vegan food store, which is 1 kilometer behind the traffic light. Suddenly it could be more beneficial to wait a little bit before the light so that you are likely to cross it with some speed, so you are a bit earlier at your destination. Let's see. In order to figure stuff out, we begin with an arbitrary speed profile as your generic plan of action. Okay, maybe use one that actually makes a bit of sense. Starting speed v0, area corresponding to track length fully maxed out before T-red is reached. Nice. Now at some point the light turns green. Let's say here. We will call the phase up to this point approach phase and color everything that has to do with this phase in red, including T green, because I decided that that makes sense. Now you hit the accelerator and accelerate with maximum acceleration until you reach the maximum allowed speed. This will be the acceleration phase. You then cruise at maximum speed until you reach the store, cruising phase. The store reaching time is the cost of the trial, so let's not waste any more precious lifetime and compute it. It is the sum of the durations for our 3 phases, so let's compute each of those then. The duration of the approach phase is obviously just T green, but we will also need the track length, L approach, that was covered in that phase, which is the integral. Now comes the acceleration phase. Acceleration is the change rate of speed, so n speed is start speed plus acceleration times time. So the duration of the acceleration phase is determined by the speed when the light switches to green, the cruising speed and the acceleration, like this. The covered track length can roughly be exactly computed as the average speed times the duration. During the cruising phase you cover the remaining track length with cruising speed. This length is the total length from the intersection where you first saw the traffic light all the way up to the shop, minus the approach phase track length, minus the acceleration phase track length. And the cruising time is this length divided by the cruising speed. Add all times up and voila! Cost time for one approach. Now, in order to compute the average cost, we have to integrate this whole thing over all possible green switching times and divide by T-red, as before. Wait, there's still room on the blackboard. Alright, so crunching everything into a single formula, we obtain this marvel here. We want to minimize it, and the thing that we can tune is the whole continuous speed function. Now, there's a way to do that called calculus of variations. But using that would be like trying to impress women by making a YouTube channel about maths instead of just going out and messing around a bit. And nobody would be that stupid, right? So I rather used the dissatisfying and annoying but working nightclub of mathematics, numerics. I assumed a quadratic function for the speed curve like this. Then I played with the three coefficients to get different parabolae as speed profile. I then limited the maximum speed and the track length, so I only get valid solutions. Then I could take a look at the cost. And guess what? It still seems that it's the best solution to race towards the light and start braking as late as possible. I was already starting to think about how I could tweak the problem further so that it finally throws out some sweet, smooth, interesting optimal solution curve that I was hoping to find in the first place. We could include the frustration as a function of how close to the color switching moment you arrive at the traffic light. But maybe it's time to give in and realize that maths does not always behave the way I want her to, and that she is right and I was wrong. This time. But that doesn't keep me from being an immature child about things, and in an RL situation I am now extra satisfied with my life when I coast across a green turning light because I slowed down early, although I'm aware it's not the best solution. And isn't conscious ignorance, despite better knowledge, what makes us human? Stupid bus, go away. Optimization criterion. You decelerate initial. Now let's take a look at the thing. Now. So then let's consider the third scenario. So we get for all others, but I won't work out the maths for all that. But that doesn't keep me from being an immature child about. But that doesn't. And Viola.